Hello viewers, I'm Kausalya. Today we are going to discuss some important terms in magnetic circuits. We start our today's discussion with magnetomotive force. So here, as we all know, this is a steel core, right? And to this steel core, I have some coils which is bound around the steel core, and through these coils I am giving a current of I amps. Because of this current in turn creates a flux, and that is denoted here as a core flux. And to the iron ring, you see this D is the diameter, okay, diameter of the cross sectional part of the iron ring. So what do you mean by this part is when you cut this iron core into two. For example, you see here, when you cut this iron part, right, into two, so what happens, this area, okay, this area will look like a circle. So this is what which is represented here as a cross sectional area. Right, if the diameter of this cross sectional circular area is d, then what about the area? So area is given by pi by 4 d square. And here the things which are shown by the blue line is known as leakage flux. Right, these are the fluxes that comes around, okay, that leaks. That's why it is named as leakage flux. And here the mean flux path. So here, since we are taking a circular core, the flux established is also in the form of circles. So how to calculate the mean flux path? So again, it is nothing but the circumference of the circle, because the flux spreads entirely in this area. Right. Therefore, the mean flux path is given by the formula 2 pi r. So now we will discuss what is a magnetomotive force. So here you see a steel ring of mean radius r meter and a circular cross section of diameter d meter with a coil of n turns wound around it, through which a current of I amps flows. So here we are having a steel ring, right? We are having a steel ring, and this circular cross-sectional area has a diameter of d. And this steel ring has these wires, okay, some wires are wound around this steel ring, or in other words, technically speaking, we can say conductors. Okay, conductors of n turn is wound around this steel ring, and through these conductors we are allowing a current I to pass through. Right. So what next happens? Whenever the current flows through the coil, this creates a magnetic flux in the ring. Right. So why the magnetic flux is created? Because the flux is created because of this current I, right, which flows through this n turns of the coil. That is the reason why flux is created. Right. Initially, when you do not supply any current through this coil, this apparatus, okay, this setup doesn't produce any magnetic flux, or in other words, this diagram, okay, this steel core doesn't have any magnetic flux inside it. But once when the current is given to this coil, automatically the magnetic flux sets up in this steel core. Right. So here this magnetic flux is generated because of this current I, and this current I flows through this coil, right? Therefore, the magnetomotive force is nothing but it is the product of this number of turns and the current that flows through this coil, right? So the magnetic flux is generated because of the current that flows through these coils. The same thing, the product of number of turns of the coil and the current is known as the magnetomotive force. So this magnetomotive force is the main reason for the production of magnetic flux in the steel core. Right. So the magnetic flux produced in the steel core is mainly due to the presence of this magnetomotive force. Can you understand what I am saying? Right, the magnetic flux sets up in the steel core only because of this current, and this current as well as only Through these conductors, the current flows inside, right? So here the magnetomotive force is nothing but this is the product of number of turns of the coil and the current that flows through the coil, right? So here, technically speaking, we can simply say magnetomotive force as product of N and I, where N is the number of turns of the coil and I is the current that flows through the coil, right? So this is the concept which I have explained just now, right? Now, what will be the unit of magnetomotive force? As I said, magnetomotive force is nothing but it is a product of N and I. N is nothing but number of turns and I is the unit of current is amps. So here the unit of magnetomotive force is given by ampere turns, right? So next, we are going to frame some formulas. So what is meant by magnetic field intensity or magnetizing force? You see, this magnetic field intensity or magnetizing force is nothing but it is the ratio of magnetomotive force per meter length of the magnetic circuit. So here it is the ratio of magnetomotive force. What is the magnetomotive force? It is nothing but the product of N into I, right? Number of turns into current that flows through the coil. So therefore here this magnetic field intensity is the ratio of magnetomotive force to the length of the magnetic circuit, right? So what do you mean by L here? L is nothing but it is the length of the mean flux path, that is the area of the steel core in which the magnetic flux gets established, right? That is known as the mean flux path, and this is equal to 2 pi r. Why this is equal to 2 pi r? Because we are considering a circular steel core, right? So here we are having a circular steel core and only the magnetic flux gets established in this path, right? So when you measure the entire length of this outer circumference, okay, we call this as a 2 pi r, right? 2 pi r of a circle or circumference of the circle. So therefore you see here H is equal to Ni by L. Ni is nothing but the magnetomotive force. So here it is simply represented as F by L. So what is the unit of F? It is nothing but ampere turns. And what is the unit of L? It is meter. So H is given by ampere turns per meter. So what is L? Specifically speaking, L is nothing but the circumference of the circle, right? So what is the formula for circumference of the circle? It is 2 pi r. Therefore, H is given by Ni by 2 pi r. So again the same unit here, right? Because 2 pi is a constant and the value of r is measured in meters. So ampere turns per meter. So the next topic is permeability of free space. So permeability of free space, again we are considering a conductor of a single turn. So what do you mean by a single turn conductor? You see, this is a conductor which has only one turn, right? So this is a single turn conductor. So you see this diagram, we have a single turn of a conductor and we are placing it in vacuum. So at C, that is a point C through which the current of 1 amps flows into the plane, right? So here just we are having a conductor, right? And this is the center part of the conductor, right? That is, this is the center part through which a current of 1 amps flows, okay? Current of 1 amps flows into the plane. And the current that flows inside the conductor returns, okay? This returns, you see, at a distance of 1 meter from the center part of the plane, right? Can you understand? Can you make a guess? Here we are having a single turn conductor, okay? We have to restrict like this. This is a single turn of the conductor and a current of 1 amps is flows into this plane like this. And the current that flows into the center comes out at a distance of 1 meter, and here I am representing that as C1. Right. So you see here, figure shows a single turn of a conductor placed in vacuum. At C, the current of 1 amps flows into the plane and the return path of the current is located at a distance of 1 meter from C, and here it is denoted as C1, right? Now for this circuit setup, for this single turn conductor, we are going to calculate the magnetic field intensity. So here the magnetic field intensity is given by the formula just now we discussed, right? H is given by Ni by 2 pi r, right? So here again you see what is the radius. Here the value of radius is 1, and what about the number of turns? Again this is a single turn conductor. N is also equal to 1 and the current that flows is also equal to 1 amps. Now we are going to substitute these values in this formula. Therefore, the value of H is given as 1 into 1 divided by 2 pi into 1. So, simply it is given by 1 by 2 pi ampere turns per meter. So, this is the permeability of a free space, okay, right? So, now we are going to discuss about relative permeability, right? So, what is meant by relative permeability here is, you see, the same setup. Okay, just what we see, the same thing. You see, the magnetic flux inside a coil is increased when an iron core is inserted, right? So now we have a single turn of a conductor, right? Just now we have seen we have a single turn of a conductor and we are passing a current of 1 amps through the center, and the return path of the conductor occurs at a distance of 1 meter. Okay, the same thing. Here the magnetic flux produced, okay, the magnetic flux produced gets increased when an iron core is inserted. Okay, if you place an iron core, right? If you place an iron core in this setup, automatically the flux produced gets increased, right? So, you see, the ratio of the flux density. What do you mean by flux density? Flux density is nothing but flux produced in an area. Okay, that is known as flux density. So, the ratio of the flux density produced in the material to the flux density produced in vacuum by the same magnetic field strength is termed as relative permeability. So, just now we discussed, right, permeability of free space, the same thing. So, here we have taken the values, right? So, the flux density produced in a material to the flux density produced in vacuum, we are comparing, right, by the same magnetic field strength, right? So, here the ratio between these two factors is known as relative permeability. So, what do you mean by permeability? The ability of a material, okay, ability of a material to allow the magnetic flux to pass through it is known as permeability, right? So, here the thing what does this indirectly says is, whenever we have a iron core, okay, whenever we have some ferromagnetic material core, automatically the flux produced gets increased, right, when compared to the flux produced in vacuum. So this is the key concept here. So here for air, what is the relative permeability? It is equal to 1. Whereas for nickel iron alloy, you see, it is 10 to the power 5. You see how much drastic difference it creates, right? So we always need a very high amount of magnetic flux to be produced. Yes or no? Because this is what we need. Therefore, for nickel iron alloy, the value of mu r is 10 to the power 5. So, when we are going to apply in the formula. So, B is equal to mu into H. So, what is mu? Mu is nothing but it is the product of mu naught and mu r. So, mu naught is the permeability of free space and mu r is the relative permeability. Okay, just now we discussed, right, what is permeability of free space and relative permeability. So, here you see for magnetic materials, the values are given as the relative permeability values varies in the range of 600 to 10,000. And whereas in a non-magnetic material, the value of mu r is taken as 1, okay, the minimum value. So, that's all in this video. If you have any doubt, let me know in the comment section. Thank you.